Hello everyone, this is Vipradatta and I'm teaching you quantum mechanics. Welcome to your own channel, Paper Muni. Today is lecture number 23.
Morning, sir.
Good morning. All right, so last class we did the how to place the particles in a given potential. All right, now let's do a revision problem. All right, so let's start this today's lecture. Now the question is, question is given to you as this. Now this is a revision problem. Okay, there is a revision problem. All right, now the question says that the ground state wave function of a particle, the ground state wave function of a particle, all right, in a three-dimensional potential, in a three-dimensional potential is given by psi r is equal to a e to power minus a square. All right, so this is a. Now where a is the normalization constant, a is a normalization constant, and the value of a is given by the value of a is given by. All right, so option A is alpha. Okay, so this is okay, let's write it in a only, small a. Now a by 2 pi, this is 3 by 4. B option is 2a by pi, this option, this is to the power half, and C option is 2a by pi, this is 3 by 4, and D option is a by 2 pi, 3 by 2. All right, so this is the question from HCO 2018.
So is
Right.
it a r square e to the power?
Sorry?
Is it e to the power minus a r square?
Yeah, this is AR square. This is e to the power minus a r square. All right. So the wave function is given to you, and it is asking about the normalization constant. So how will we proceed? So we know the normalization condition. Normalization condition in 3D will be what for this radial coordinate? So normalization condition. Even if we don't talk about the radial part, we just say that okay, if we want to run the normalization condition in 3D, how can we write it? So it will be psi mod square, and this is integration over all space, and this will be a volume element. Okay, this should be equal to 1, right? Is this clear to everyone? The normalization condition in 3D will be this. So this is the volume element. This is the volume element. All right. Now let's do the calculation. So if we write down the expression for this, what the wave function which has been given to us, so let's write it down. So the integration will be from r equal to 0 to infinity. Okay, r equal to 0 to infinity, and the theta will go from 0 to pi, and phi will go from 0 to 2 pi. All right, and in this we can see the wave function is given to be real. All right, the wave function is real. So what we can do is we can just directly square the wave function. Okay, we don't need to just take the mod and write it down. So we can just directly square the wave function, which is this, and then replace that. Now we know that this thing, the volume element is what? R square sine theta dr d theta d phi, right? So if you substitute this here for the volume element, you'll get this. Okay, so this is dr d theta d phi. All right, d phi is equal to 1. Now if you do the calculations, like arrange the elements according to this thing. Now radial coordinate part is this. All right, now what else we have? We have theta part, which is 0 to pi sine theta d theta, and 0 to 2 pi, this will be d phi is equal to 1. All right, now this part will give you how much? This will give you 4 pi. All right, this gives you 4 pi. So let's calculate this rest of the part, which is a square. Now this one, we have the formula for this. So gamma function will have 2 plus 1 by 2. All right, and this is the coefficient here is this coefficient is 2a. So here we'll have 2a to the power, this is 2 plus 1 by 2. All right, and multiplied by 4 pi, this gives you 1. Further, if we calculate this, a square is half. Now this will give you 3 by 2, right? 3 by 2 we can write like this, half gamma half, and divide by 2 into, now this can be written as, this will be 3 by 2, and a will have power 3 by 2. All right, so this is equal to 1. Now if you simplify it further, so what will we get? Now this is equal to root pi. So I'll just writing the solution to this directly. So this is a square is equal to 2a by pi 3 by 2. All right, we can, if you see this thing now, you can rearrange all the elements and see that you'll get this one. And finally, if you take the square root, so let's keep the positive value. Let's keep the positive value, and which has been given in the options. So this is, you get to be 2a by pi 3 by 4. This is the answer. All right, this is the answer. So is everybody getting this result? Now there is a 4 pi also here. There is, I forgot to mention this 4 pi here. All right, there's a 4 pi here. All right. Now let's go to, now this option, the option which matches is C option, right? C is correct. C is correct. Now let's start with this thing, complete wave function. Now let's talk about how does a wave function evolve in time? Okay, so far we have been dealing with the wave function not evolving. It was stationary. All right. Now psi is actually a function of, now we had discussed this the complete wave function. We had discussed the complete wave function in so during when we studied Schrodinger equation. All right, so we had this complete wave function as this, and from previous lecture of from previous lecture of previous lecture on Schrodinger equation, Schrodinger equation. All right, so what do we have now? Psi is equal to Cx, this is minus iota et by h cross. All right, so this is what you have now. We had this thing, you should like you remember, if you remember this, this was the form we had when we derived the form of the wave function from Schrodinger equation. All right, so in general, and we also wrote this thing that in general, what do we have? Psi is equal to summation n Cn. Now, if the wave function is a superposition of several other states, so we wrote this as this. Okay, so this is just from directly from the previous lecture on Schrodinger equation. Okay, so we have not added anything extra. All right, but just that we were not discussing about the time period, so time part so far. Okay, we were just concerned about the space part till now, but now we'll see how the time affects the wave function. All right, so let's take an example. Let's take an example. All right, so 1D, say let's take an example of 1D box potential, 1D box potential of width L. All right, 1D potential of width L. Now energy eigenfunction, energy eigenfunction. All right, so energy eigenfunction, we know that this is psi n is equal to 2 by L root 2 by L sine n pi x by L. All right, where n is equal to 1, 2, 3, and so on. All right, so this is clear. Now, in this case, what we have is we can write, we can take this, say, this equation, we take it to be, say, this is 1. All right, let's write it to be 1 because we will refer it to in the next few steps. So this equation is, say, 1. Now expression is 1. Now at time t, what will happen? At time t, we can write psi n xt as 2 by L, okay, sine n pi x by L, okay, e to the minus I iota e n t by h cross. All right, so we just put, what did we do? We just used the space part and combined it with the time part. All right, so this is the complete wave function for the particle in a 1D potential. All right, now en is written as usual what we had in the formula. Okay, so this is n square pi square h cut square 2 ml square. All right, now equation 1, like this the equation which we refer to it as 1. Now this can be written as, now this wave function, now this wave function can be written as in the following manner. Okay, so this can be written as this. Psi, we can write that at 1 can be written as psi x. Now if we put t equal to 0, if we put 2 equal to 0 in this expression, what will happen? So this is psi n and we put x t equal to 0. So this will give us 2 by L sine n pi x by L, and which is the space part. Now this we get back the space part as it is. Okay, if we put t equal to 0, we get back the space part of the wave function. So we could have written this wave function as this as a function of time where t is equal to 0. All right. Now let's talk about some problems which will use these concepts. Okay. So now the question is, now the question says, uh, now this is exactly what we have discussed right now. This is the question is based on that. So the wave function all right, psi of a quantum mechanical system of a quantum mechanical system is described by, cannot, there is no is here, so described by a Hamiltonian okay, Hamiltonian H cap can be written as a linear combination all right, of phi 1 and phi 2, all right, which are the eigenfunctions of H, which are eigenfunctions of H, which are the eigenfunctions of H, Hamiltonian operator, with eigenvalues E1 and E2 respectively. Okay, E1 and E2 respectively. Now at t equal to 0, the system is prepared in the state all right, psi naught is equal to 4 by 5 phi 1 plus 3 by 5 phi 2, and then allowed to evolve with time, and then allowed to evolve in with time. All right, so the wave function at time t is equal to half h divided by E1 minus E2, all right, will be. Now this is accurate to within a phase. All right. So this question is from TIFR. This question is from TIFR. All right, this is 2010. Now let me write down the options. So option is, first option is, this is 4 by 5 phi 1 plus 3 by 5 phi 2. All right, B is phi 1. Okay, C is 4 by 5 phi 1 minus 3 by 5 phi 2, and D option is phi 2, and E option is, okay, E option is, this is 3 by 5, okay, phi 1 plus 4 by 5 phi 2, and there is F option also, which is 3 by 5 phi 1 minus 4 by 5 phi 2. All right, so this is the question. Now let's see how to solve it. Now the process to do these kind of problems is the following. Okay, so I hope the question is clear to everyone. It says that the system is, now these are the details which they just try to build up the things, like just to tell you that phi 1 and phi 2 are eigenfunctions of the energy of the Hamiltonian operator. So that is fine. Then you have the eigenvalues, okay, E1 and E2. So at t equal to 0, the system was at this point. This was the wave function of the system, all right, when it was prepared. Now and then it was allowed to evolve in time. We just leave the system and let it do whatever it wants to. Now the wave function at time t, the t value is given to you, this specifically given to you, that this is the value of the time. Okay, so then at that point of time, what will be the wave function, the complete wave function? All right, not just the space part, we will also include the time part. All right, so let's see. Now what will happen here is, this is the you can solve most of the questions by using this technique. All right, so let's write down the complete wave function. Okay, let's write down the complete wave function, which is that including the time part. So this first one, all right, so okay, so in this case, okay, let's write down this thing first. So we have this thing, we have been given that h operating on phi 1 is equal to E1 phi 1. All right, and this is given to you is this, uh, okay, before going into this question, it's better if you just solve a easier problem than this, then you have a picture of it. Okay, let me put this down and give you another question, so that you are on able to get, if you're doing it for the first time, so it's sometimes difficult to grasp the concept. So let me give you a question, an example question. Okay, it's some simpler question. Okay, so consider a 1D box potential of width L. Okay, the wave function, all right, of a particle at t equal to 0 is given by psi x 0. Now this is for the time part, is equal to 1 by root 3 phi 1. Okay, root 3 phi 1, 1 by root 3 phi 1 plus 2 by 3, this is phi 2. All right, where phi 1 and phi 2, where phi 1 and phi 2 are the ground state, are the ground state and first excited state of 1D box, All right, now write down, now this is a very straightforward question which everyone should able to do it. Write down the wave function, write down the wave function of the system, of the system at any time t. Okay, this is a straightforward question. I have to just write down the wave function at any time t. All right. So just write down the wave function. How will it look like? So the wave function will look like this. Xt will have the, now the wave function is already normalized. Okay, so we don't need to worry about it. Now this, the time part, if we add the time part, we have to add E1 here, E1 by this one, h cross, plus root 2 by 3 phi 2 e to power minus iota e2 e by h cross. All right, so this is the wave function at time t, right? So I hope that this is clear to everyone. Now, this is the answer to this question. All right. So what we did, we took this state and we wrote the corresponding e values here. Okay. So these are the values corresponding to each of the states. Okay. This is what we do for time. Just if you want to write down the wave function which depends on time. Now let's talk about the problem at hand. Okay. So this was the question. All right. So let's start. Now in this case, what was there? We had this thing that it's given to us that h operating on phi 1 will give us E1 and phi 1, and also we have been given that h operating on phi 2 will give us E2 phi 2. All right. Now, if you write down the wave function which is given to us is this 4 by 5 phi 1 plus 3 by 5 phi 2. Right, this is the wave function given to us at time t equal to 0. Now, next, if we write down the wave function at any time t, at any time t, all right, so psi t, all right, psi t will be 4 by 5. Now they have used the notation here, which this represents that there is t equal to 0. All right, so I use this thing at t equal to t. Okay, this notation is for time t equal to t. All right, so this will be 4 by 5 phi 1 my e to power minus iota e t, now this is 1 by h cross, all right, plus 3 by 5, okay, phi 2 e to power minus iota e2 t by h cross. All right, now if you the process is in this kind of questions, you just take this common. So let's keep psi t here. Just take one of the components common, one of the exponential part common, okay, from the whole expression. So let's take this one. Let's take this component to be common. Okay, in this case, we take this as common and take it out from the expression. So if we take it take this out, so we'll get e iota e to power iota minus iota e1 by e1 t by e1 t by h cross, and we have 4 by 5. Okay, now this will be phi 1 plus, in this case we have 3 by 5. We have 3 by 5. Okay, and next is phi 2. This remains as it is. Now this express this when we have taken common this factor. Okay, we have taken this factor common. So what we have is we have to subtract it from this part. So for the from the exponential part. So what we'll have is this iota. This is e2 minus e1. All right, and et t by h cross. All right, so this is what we have in the second term. We just took this common. If you multiply this, you'll get back this equation. Okay, the previous one. All right. Now, what we have to do, we have to check what happens to the equation at t equal to capital T, which is given by, it's given in the question that half h by e1 minus e2. So if we do this in this above expression, so be careful with the exponential part. All right, so there's lots of powers here. So in this case, we substitute wherever the t is, we put this value. All right, so we are doing it at t equal to capital T, which is given by this. All right, now if you substitute this expression, now this is e to power, this is iota e1, Now instead of t, we'll write down half h, okay, divided by, this will be uh, h cross, and we have e1 minus e2. All right, this is the first term, which the common term which we had taken out. Now the next one is 4 by 5 phi 1 plus 3 by 5 phi 2. All right, in this case we just substitute whatever we have been given for t. So e2 minus e1. All right, and now there's the h cross below, and in this case we have half h by e1 minus e2. All right, so if you solve this, now this is, everything is in power though. Now the this is in power to exponential. This is the power to the exponential. All right, so don't get confused with the notation, the powers. So then now just solve this. So what will you get? The first term you get is this one. Now this is a kind of a phase. This will adds phase to the uh, wave function. Okay, now let's ignore. Now it's, the question says that you can ignore this thing. Okay, so ignore means to some order. It says that accurate to within a phase. So this is a phase, and let's not worry about it. So because we just have to give the form other than the phase. Okay, we don't need to worry about the phase here. So let's keep it to be c.
Sir,
Okay, yes.
sir, I didn't get that part, sir. Can you repeat it again?
So it says that to accurate to within a phase.
Okay,
Okay,
why are you calling that the phase, sir? The first term.
because it's what happens, like if I give you a wave function which is say a sine x. Okay, so
Yes.
what will now if I put a is equal to minus a sine x,
Okay.
so this part is called, this changes the phase. Okay,
Inverted.
it gets inverted. So this is a phase. All right, this is how it's called a phase, just a name given to it. All right,
Right, sir. All right.
so in this case we just take it to be common because it doesn't talk about the phase, it doesn't include the phase. Okay, it just says that there is a phase, but we don't need to worry about it. We want to get the other part of the wave function, okay, which is the phi 1 and phi 2 part. So what happens here is this 4 by 5 phi 1 plus this will be uh, this is 3 by 5 phi 2. Now if you see, if you calculate this thing, what will you get here? If you see this calculation, this gets cancelled, this gets cancelled. All right, now what do we have? What do you have here? There's h by 2 pi, h gets cancelled here. Okay, so we are left with 1 by 2 also gets cancelled, so you are left with e to power I pi. All right, in this case you are left with minus I pi. Okay, so this phase could be minus or positive plus. We are not worried about it. Okay, because the question doesn't ask about it. All right, now now there is no minus here because this will give us, if when you substitute this will not be minus, it will be plus iota pi, because there's the e2 minus e1 and there is e1 minus e2. So if you cancel this, you get minus 1 here. Okay, so that becomes plus. So this is what we have. And what is the value for e2 or iota pi? Okay, so this is cos pi
minus
plus
1.
I sine pi. This gives you minus 1. All right, now if you substitute this, so you get psi t is equal to c 4 by 5 phi 1 minus 3 by 5 phi 2. So, and you also remember this thing, this is like Feynman called it one of the most beautiful expressions in mathematics, which is e to the power iota pi plus 1 equal to 0. Okay, it has almost all the important constants together related to each other. Okay, yeah, Euler number, iota, pi, 1 and 0. All right, so that's a different thing, it's coming from this. Now we see that this expression, now which option matches this thing? This is 4 by 5 phi 1 minus 3 by 5 phi 2. 4 by 5 phi 1 minus 3 by 5 phi 2. So this one is the correct answer, which is C option. So in this kind of question, you just have to take one of the exponential factors common and then simplify the expression. All right. Now this was the phase we are talking about, the coefficient which was coming outside. All right. Now, see, when we write a wave function, we write it like this, say a sine omega t plus phi. Okay, so this is the complete, this is the complete phase. Okay, so, and this is the phase constant. So it says that to a certain phase, okay, to a certain phase, we just need to worry about this part. So that is why the question asks for that, wrote that line. Okay, we need not worry about what is the phase actually. We just want what is the form of the superposition. All right. Now let's do another question. Now in this case, what we have is question number, yeah. Let's write down the question first. Now it says that question, the state of a particle, the state of a particle of mass m in a deep square well potential, okay, deep square well potential extended from x is equal to 0 to x equal to L is given by psi x 0 is equal to 1 by root 2 phi 1 plus phi 2. Okay, at time t equal to 0. All right. The value of x for which the value of x for which the value of so the value of x for which the value of the wave function, the value of the wave function all right will be the same at t equal to 0 and t equal to, this is 2ml square divided by pi h cut. All right, will be. Okay, so let's see what are the options given to you. Option is 0 comma L by 2. B is, this is 0 comma L. Now C is L by 2 L and D is L by 4. Okay, so I hope the question is clear to you. It says that it's the potential is the 1D box, infinite potential well, 0 to L, and the initial wave function is given to you. Okay, at t equal to 0. Find the value of x for which the value of the wave function will be same at t equal to 0, and given t is given to you some other time, and you have to say that okay, what are the values of x for which the wave function will become same in both the cases, at the initial time and the final time. All right. we need to find the value of x. So what we need to do is we just write down the wave function, okay, that complete wave function, and proceed the way I told you earlier. So at t equal to 0, we have psi, x 0, okay, equal to 1 root 2. This is phi 1 plus phi 2. All right. Now at any time t, at any time t, all right, which is psi x comma t, all right, this gives you, like, this is equal to 1 by root 2 phi 1. This, let's add the time components, minus iota e1 t by h cross, okay, this, and plus phi 2, all right, e to power minus iota e2 t by h cross. All right, so this is the wave function at any time t. Now what are the things given to us? We have been given that t, we want to find the wave function at this time. All right, and what are the other information do we have about e1? We have this value. Now this is pi square h cut square by 2 ml square, and e2, we have this value. E2 is the first excited state. This is 2 square pi square h cut square by 2 ml square. All right. Now we have all the things required here. Now let's talk about the wave function at this time. Okay, we need to find the wave function at this time. All right. So this looks really bad. All right. Now let's write down the wave function at this time. So this will be, this is psi x t. Now t is equal to 2 ml square by pi h cut. All right. So this is the time at which we need to find out the expression. So let's write it down. Now the wave function is already normalized, so we need not worry about it. So this will be, the first term will be phi 1. Now exponential minus iota. Now instead of this, what we have is pi square h cut square by 2 ml square. Now in this question, we don't need to do as I told you earlier. Okay, so this will be, just substitute this value. Okay, so what do we have here? That this is pi h cut. All right, and the other term, which is phi 2. See, when you the method I taught you earlier, we didn't know the values of e1 and e2. All right, so that is why we took the one of the factors common. In this, we already know what are the values are, okay, for energies. So in this case, you just substitute the values. Okay, so what will you get? This is 2 square pi square h cut square by 2 ml square. Okay, and here it will be 2 ml square by pi h cut. All right, so this is the expression from the previous line. Now if we solve this, so what will we get? If you solve this thing, if you solve this, you'll get as this is phi 1, okay, e to power. Now if you cancel this out, so what will you get? Now if you cancel these things, now this cancels out. Okay, this part cancels out, this cancels out, here also this cancels out, and one of the terms gets cancelled here. So what we are left with is, now let me see if the question is all correct. Yeah, the question is fine. Now if we see what are we left with now, I think there is some h cross missing in the t term. Okay, otherwise there
सर
will
h क्रॉस स्क्वायर होगा.
that will be a h square, right? This should be a h square. Okay, this should be h square.
नहीं
Otherwise,
सर वो सही है. वो
ये सर वो डिवाइड में है ना ऊपर.
डिवाइड में वो h क्रॉस है तो वो हो जाएगा इसमें.
एक मिनट. So
t
let me see. So what we are left with now, divide में h cross square नहीं है ना, ऊपर में square है.
नहीं नीचे एक और h है.
t का h क्रॉस और वो
अच्छा okay. There is another h cross ना, t का h cross और 1 by h cross और एक है ना यहाँ पे. Yeah. Sorry. So I thought I had missed that. So h cross यहाँ पे भी है. All right. So I left that out. So in this case, तभी मैं बोला कुछ इसमें like कुछ problem तो नहीं आ गया. So that's why I checked the time. Now this one is iota pi. Okay, and the other term is, this is pi 2, and this is e to power I. Now this is a minus sign here. Okay, this is what we get from this calculation. So we can write down, this is 1 by root 2, 1 by root 2. This is minus phi 1 plus phi 2. All right, so we know this, that since e to power iota minus, like e to power minus iota pi is minus 1. Okay, there is minus 1, and e to power minus iota 4 pi is equal to 1. All right, so we get the equation like at this point. Now what we have from this thing, at we have to compare. Now we have to compare expressions of initial time and this time. Okay, so the initial time we had this wave function. Now it says that the question says both should be equal. This time and this time. All right, t equal to 0, and this is t equal to 0. All right, so let's write it again. This side is psi x t equal to 0. All right, now this is given according to the question. According to the question, this is the what we need to do. According to question. All right, so let's see what happens. Let's place all the values here. So in this side we'll have 1 by root 2, phi 1. Now let me have some water. So in this case, this phi 2 is equal to 1 by root 2 is minus phi 1. All right, minus phi 1 plus phi 2. All right, now what do we have here? Now if you see this, what do we get in this thing? If you, now everything gets cancelled out, what we are left with is that 2 phi 1 is equal to 0. So that brings us that phi 1 is equal to 0. Now this implies that, now what is phi 1? This is phi 1 is sine pi x by L is equal to 0. Right? Now what are the solutions possible? So for this thing, for this we have this, that pi x by L should be equal to, now we are not using n here, we are using m. Now n we have already used for the wave function. What we are trying to find out is not the solution to the wave function, we are trying to find out what are the values for this expression. Okay, so this is the final expression, so that is why I'm using m here. Now m could be any integer including 0, okay, in this case. So what is x? X is equal to now ml. Okay, x is equal to ml, and x lies between 0 and L. Okay, x lies between 0 and L. So what are the values x can take? If you see this, what are the values x can take? Okay, x can take Now in this case, m can be what? 0 and 1. M can be according to, because it is restricted, the values of x are between 0 and L. It cannot be more than that. So what are the allowed values of M? Allowed values of M are 0 and 1. Okay. In this case, the allowed values of the solution to the equation is, it could be any values like this. Okay. M. But since x is restricted, okay, so the M allowed values of M are this. Allowed values of M. Now, this has nothing to do with the earlier solution which we did for the wave function in the Schrodinger, the 1D box. Okay, this is just a expression which is concerned with this problem only. All right. So allowed values of M. Okay, so we have 0 and 1, which gives us, which if I put this thing in the equation, which gives us that x can be only 0 and L. All right. So if you see the solution, which is, the answer is B option, right? Answer is B. B is correct. So according to the question, these are the values of x, where both the wave function at two different times, the initial time and this final this some time which is given to you, it will be equal. All right. Now let's talk about the stationary states. What are stationary states? For time evolution, these are the patterns you get. Okay, these are the two. One of the two will they'll try to invent something different, but it will be a mathematical complication rather than a physical one. Okay, just go through these two problems again if you were not able to follow anything from there. Okay. Uh, the time evolution questions usually comes in just TIFR and CISR, net and GET. Okay, this is one of the favorite questions types. So make sure you understand this time.
Hello, sir.
Yes. Tell me.
Hello.
Yes.
Sir, in the previous question, is there mentioned that phi 1 is the energy eigenfunction? You have used the phi 1 is the energy eigenfunction formula, root 2 by L sin pi x by L. In the question, is it mentioned that phi 1 is energy eigenfunction?
No, it is not mentioned, but in this type of questions, it's already given to you that the particle belongs to this thing. Okay, the particle belongs to this format, this thing, that 1D potential. So it's obvious sometimes you can see that if you are writing the wave function like this, so these wave functions are you get it by solving Schrodinger equation, right? And when you solve the Schrodinger equation and get the psi, it is usually it is not usually, it is always the energy eigenfunctions. All right. So phi 1 and phi 2 from this question is basically, yeah, it should have been mentioned. It should have been mentioned that these are the energy eigenfunctions and these are the things. But we are already discussing the energy eigenfunctions. So from that point of view, you can safely assume it to be phi 1 and phi 2. All right. But in question paper, it will be mentioned exactly. Right. Maybe I missed that line. Okay.
Okay, thank you.
So if psi is normalized, if psi at t equal to 0 is normalized, if psi at t equal to 0 is normalized, so we can write psi x0 is equal to a x, like this. We can write like this, right? X is the x part of the wave function. So let's because there is no time part, the exponential part will vanish, not vanish, in fact it will become 1, so it won't appear in the wave function. And normalization condition, as we know it, normalization condition, all right, it's given to you that minus infinity to plus infinity and psi x0 dx is equal to 1. All right. Now wave function at any time t. Let's write down the wave function at any time t. wave function at any time t. All right. So what do we have? Psi x t, psi x t is equal to a x e to power minus iota e t by h cross. All right. This is the wave function at any time t. Now, if we talk about the probability density at any time t, let's talk about the probability density at any time t. So this is the wave function mod square. Now this will give us psi conjugate xt, and we have psi xt. All right. Now let's put down the like the explicit value of psi. So x, now this part is the real part. So what will happen is conjugation will be happening in the exponential part. So this will give us et. Now iota, this minus iota will become plus iota, and this part remains as it is. The other part remains as it is. So this is x e to power minus iota expo e t by h cross. All right. So in this case, what we get? But you get x. This is, you get this square, right? Because the exponential terms get become 1. Now this is equal to this value is equal to what? This value is equal to the wave function at initial time mod square. All right. So we can see that this result, that if we have the probability density is equal, we also have the normalization condition equal. Okay. So this is equal to minus infinity. All right. So psi x0 mod square tx is equal to 1. All right. So what does it imply? Let's write it down. So note, all right, number 1, if the wave function, if the wave function is normalized at t equal to 0, at t equal to 0, it will remain normalized at any time t, at any time t. Okay, which we are seeing here, that if the wave function is normalized, then if you try to get the normalization, like if you want to check whether the wave function at time t is normalized or not, if the wave function is already normalized at t equal to 0, it will remain normalized forever. Okay, you don't need to worry about it. Now these type of eigenstates, these type of eigenstates are called stationary states. Okay, are called stationary states. Now it feels good when you are studying the theory and able to solve the problems, but it will not feel good if you don't keep revising or remembering things. Okay, after some time you will not be able to solve the problems, which you are able to do it right now. So please look into your notes whenever you say there. I know everyone has a lot of things to do, but always understand that everybody is working towards one thing, like you, like thousands of people, other people. So some or the other, they are managing things. So you also need to manage things. Okay. What is your priority? Depend. Yeah, if you are appearing for your finals, make sure that you score well. Okay, don't ignore your finals. and who those who are already like they have dropped a year for this preparation, make sure that you don't lose this opportunity. So probability density also remains constant. Okay, so these are known as stationary states. All right, now let's go for some new topic, uh, which is step potential. All right, step potential. Now this is one of the simplest barriers you can have. Now what let's see how does the step potential look like what kind of step potential do we have in classical mechanics. So let's talk about that first. So classical step potential, and from this we'll also learn about some of the terms which we'll be using in analysis of the quantum mechanics, quantum mechanical step potential. So if we talk about the classical step potential, okay, so we can see this, we can visualize this. Okay, that's why it's better to start with this. Now this is the what I'm going to do is this the real experiment which you are doing. Now this is not a 1D this is not a 1D experiment because when you roll a ball, say you have a hill here. Okay, let's talk. There's a hill here. Okay, this is a ground level, and then there's a hill. Okay, and this has some height h. This has some height h. Okay, and let's say we have a ball here. Uh, we have a ball here, and we are giving it energy. Say E is equal to, now let's talk about that this V, the potential energy here is equal to 3 joule. Okay, the potential energy here is 3 joule due to gravity. All right, gravitational potential energy. Now PE, the potential energy here is 0. All right, at this level, the reference point. Now let's say that this is x equal to 0. Let's say that this is x equal to 0. Now if I give the ball this energy, now this is a real experiment, this is not a graph, this is a real experiment which you are doing, and this is not a you can think of it as a you can think of it as a 1D potential, but actually the experiment is not 1D. Okay, but if you see from one side, okay, like this, you can think of it that way, but this is a real experiment, this is not a plot. All right, so you have this hill rising, the cross section of the hill showing to you, and you have been you give this particle this energy and it moves this way. All right, so let's see what happens. So in this case we are defining the potential to be this. So we have Vx is equal to 0 for x less than 0, right? That is true. We have the P potential energy is 0 here. Now this potential energy is actually here Vx. All right, so what happens is Vx is gradually increasing. We are changing the Vx gradually in this case. So Vx is gradually increases in this case, gradually increases to V naught. All right, we don't have any equation for that to represent that change. That will be some function of the height, right? Now what happens is let's draw that, let's do this thing, this experiment, and then represent it using graph. Okay, so graphical representation. Okay, graphical representation. So in this case, let's just convert the experiment to a graph. Okay, so we have this graph. Now this is Vx. On the y axis we have the Vx potential energy, and the x axis we have the x position, okay, at a given time. Now this is the potential energy is changing like this, right? Potential energy is changing like this for the hill. Now what happens is, say the energy is given to you. Now energy, if you represent it graphically, now the ball is not floating in air. Okay, the ball is not, we are not talking about the ball here, we are talking about the energy of the ball. Okay, so which we had given to be 2 joule. All right, now this is purely kinetic energy in this case. because V here is 0. Vx at this level is 0. Okay, and here it is V naught. Okay, so in the now this is Ke, this was completely Ke, and this is say a function of x. Of course, it's changing with x, and let's talk about this. That what happens when the ball reaches here at this point. Say the ball starts from here and it reaches somewhere here. All right. So what will happen here? Okay, if we have the ball coming up here, so in this part, this part will be the kinetic energy of the ball, and this part from the graph, it is the potential energy. All right, and the total energy remains constant. The total energy remains constant throughout. All right, now what will happen if this is x equal to 0, this part is x equal to 0, x equal to 0. All right, and say when it reaches this point, this is say xt. Now when the ball reaches here, what will be the value of the kinetic energy? It will become 0, and the potential energy will become whatever the value of potential is, right, at this point. Now let's see what does it mean. What will happen if it reaches that point? What will happen after that? The ball will again roll back. The ball will again roll back from there in this direction. All right, it cannot go further than that. It cannot climb the wall, right? Climb this potential. So let's see what happens. So case one, in this case, what we assume is E is less than V naught. All right, E is less than V naught. And so have you drawn the diagram?
Yes, sir.
Yes, sir.
All right, so E is less than V naught, and after reaching, now what does it say? After reaching xt, from the graph we have, after reaching xt, after reaching xt, all right, now which is the classical turning point, which is the classical turning point in this case, classical turning point. All right, now the particle will roll back down. The particle will roll back down. All right, this is called, this thing which is happening is called, this is called reflection, or the particle is reflected. Okay, reflection. So the particle gets reflected from that point. Okay, it reaches that maximum, the point where the total energy allows it to, and then it goes back. So we say that it's getting reflected from the potential. Okay, so this is how we talk about the reflection. Now what about the next case? This is the next case. Say in this case what we have is case, this is case 2. All right, so E is greater than V naught. E is greater than V naught. All right, this case, what happens? Let's see. So let's draw the graph again. So this is Vx. All right, and this is x, and we have the potential as earlier, the same way. Okay, and let's say the energy at this time is this, at this level, the energy of the particle. Now the particle is along the x-axis, it's moving along the x-axis, it's not just rising above in the air. This is what we are representing as the energy. All right, so the energy here is purely kinetic energy. All right, this is purely kinetic energy. There is no potential energy involved because here at this level the Vx is 0 at this level. At this level Vx is 0. Now what happens here? All right, so this is say 3 joule as per our example. Now the energy is given to be 4 joule. All right, the total energy is 4 joule. All right, and this is V naught. So when the particle reaches here at this point, the particle is here. All right, now for this particle, the energy, this part will be the kinetic energy. This part will be the kinetic energy. All right, and this part is the potential energy. All right, which is equal to V naught in this case. Okay, which we have labeled it here. Now this we are considering that this becomes flat and remains so. So in this case, this is the energy distribution for the particle. Now x is equal to, this is x equal to, now whatever we are discussing is completely classical. All right, there's no quantum mechanical part here. But here the terms which we'll be using is same, the reflection part and the transmission part. Okay, now according to the example, which we have taken here. Okay, kinetic energy after reaching the potential step. All right, we are calling this a step. Okay, it's rising our level, so this is kind of a step. So the kinetic energy in this example is what? Is E minus Vx. Okay, E minus Vx. Now what will be the kinetic energy here? Now E is 4 joule and this is 3 joule. Now the kinetic energy is 1 joule in this example. All right, so the particle is able to move beyond the step, so it can continue to move. The particle will move with some kinetic energy, all right, move with some kinetic energy and will not return back in the region. All right, which is x in the region x, this x greater than 0. Like it will keep on moving, will not return back in this region. Okay, in the region x greater than 0, it will keep moving in this region. Or it's becoming misleading. It will not return back. Okay, you can write it here in region x greater than 0. All right, now, or okay, let me write it here. So it will not return back to the region x less than 0. Okay, it will not return back, it will not come back from where it came from. Okay, it will keep moving forward. Now this is called, this thing which is happening here, this is called transmission. The particle is getting transmitted, okay, in the potential given. So these are the two things which we want to take forward in this in the quantum part, the transmission and the reflection. Okay, and things will change in the quantum thing. Like this is obvious that if the particle has a higher energy than the potential, it will of course move forward, it will be transmitted. And if the particle has lower energy than the potential, it will be reflected. Okay, so this is obvious now, because we already know what happens here. Okay, from our experience, day-to-day experience. Now in quantum mechanical step, how does it change? Okay, let's see the quantum mechanical step. Quantum step potential. Step potential. All right. Now, what is how does it let's define this thing. Now, what we do is we try to simplify the problem. When we learn something, we simplify the problem. Instead of a variable slowly varying v, which we treated in the previous example, what we do is we take it like it changes abruptly. Okay, so let's draw the potential. So let's define it mathematically first. So Vx is equal to 0 for x less than 0, and equal to V naught, and equal to V naught for x greater than or equal to 0. All right. So let me have some water. So the diagram is let's draw a diagram. Now this is the graphical representation of a 1D potential. Okay. So this is x. Okay, the particle moves along the x-axis. Okay, it's not anywhere else. Now this is Vx. So the potential is this. This is the potential which we have here. This is the potential. Okay. This is the potential, right? Now x is equal to 0. This is x equal to 0. X is equal to 0. All right, and this is V naught, and with let's say that the energy, initial energy of the particle is here at this level. Okay, so this is say energy E, and this is V naught. Fine, and we have the kinetic energy on this case. The K. This is purely kinetic energy initially, and what we have here is, so if the at this level, at when the particle, if it reaches here, now it will always reach here. No, there is no problem about it. So this is E minus V naught, and this one Vx, okay, which is equal to V naught in this case. All right, this is a situation which looks exactly similar to the classical thing. Now let's call this region. Let's call this region 1, and this region as region 2. All right, let's put it somewhere else. So this is region 2. So the graph looks like same as the previous one, just that we have taken the potential to be very simplified form. We are not considering it to be a function of x, like it is a function of x, but not in the way it's varying gradually. It's abruptly changes from 0 to V naught. Okay. Now, what happens in the quantum mechanical step? What happens? Now let's see. So case 1. So this is the case 1, which is where we have, this is case 1. All right, E greater than V naught. All right, E is greater than V naught. So let's what happen. The energy is more than the potential given to you. So what happens now? Every potential we start discussing, it boils down to one thing, that is the solving the Schrodinger equation. Okay. Now in region 1, okay, the time dependent, now time independent part, we are just solving the time independent part. Okay, now time independent Schrodinger equation. Independent Schrodinger equation. All right. So what do we have here? Now, if we write down this in this region, so minus h cut square by 2m, this is psi x divided by dx square, okay, dx square plus vx, this is psi 1 x is equal to e psi 1 x. All right. Now, what happens here? So we know that this in this region, it's given that Vx is equal to 0. Okay, in this region, since Vx is 0, so what we get from this equation, we can write from this equation, putting Vx equal to 0, we get minus h cut square by 2m, and this is double derivative with respect to x equal to e psi 1. Fine. Now let's simplify this further. So what we get is now this equation we have already come across in case of free particle, okay, as well as 1D box, but the boundary conditions were different. Okay, so this is the same equation which we wrote several times, and let's simplify this further again, just including the k this time. So we can write this is okay, this is equal to minus k square psi 1. All right. Now k here is root 2m e by h cut square. All right. So what is the solution available here? The solution is, if you write down the solution, e to power I kx plus b e to power minus I kx. All right. So we have h less than 0. So I think I'm sounding a bit heavier. So it's like for teachers who teach like in coachings and all, they have to take care of their throat like the way the singers take care of their throat. Okay, because you have to keep speaking continuously for 6-7 hours. So I just drank cold water previously, so that made my throat. Sorry for the interruption. Now it feels better. All right, so you have this thing psi 1 is equal to this. This is the solution which we have from the equation. Now, what can we say about it? All right, so this is the wave function in the of the particle in the region 1. All right. Now in this case, let's analyze the situation, what the results. Okay, so what we are doing is, we are in this case, we are sending a beam of particles, all right, in the same state, with same velocity. Okay, so when we in this case, we are not just speaking about a single particle, we are talking about a stream beam of particles. Okay, So this wave function represents the whole collective beam, and we are sending it with the same velocity. All right. Now each incident particle, each incident particle, each incident particle each incident particle can be represented by
Sir,
yes.
so what is the first statement?
The first statement is, in this case we are sending a beam of particles in the same in the same state. Not, this is a state missing here. In the same state. Okay, in the same state with same velocity. All right. And each incident particle can be represented by psi is equal to e to power I kx. All right. So each of them can be represented by this wave function. Now also we can represent this thing, the incident. Now there is a difference in the interpretation. Now there will be a change in the interpretation. This thing, we are saying that each incident particle can be represented by this wave function psi, which is a e I kx. That is fine. Now if I say that the incident particle, the incident beam, now I'm talking about the beam, incident beam of particles, incident beam of particles is represented by psi is equal to e to power I kx. All right. Now there are two different things. This wave function, there is a difference in this. This wave function represents one particle, and this represents several particles. All right. Let's see how it's different. Now in this case, the meaning of psi square changes. In this case, when we talk about the beam, which is represented by this wave function, the meaning of psi changes. In this case, the meaning of psi is this. Earlier, when we represented only one particle, the meaning of psi mod square was the probability of finding the particle. Now in this case, the meaning of psi mod square is equal to, like, you can write like this. In this, the interpretation becomes this: the number of particles per unit length. Okay, when we use the wave function for the beam, we define the psi mod square as the number of particles per unit length. Right. So it's no more the probability. It's of course related to the probability. It is of course related to the probability of finding the particles, but it is not directly interpreted as that. Okay, we'll see how it's, because we'll also see what is a probability current. In that case, it will be more. In that case, you will understand better what does it mean. All right. So in region 2 next, let's go to region 2. What happens there? Region 2. Region 2, the time independent. Okay, let's discuss region 2 tomorrow. So any doubts so far? Any comments? All right. So if there are no questions, then we can sign off.
Sir?
Yes.
So is it possible to upload the video by evening? I'm just asking, sir. If it's not possible, it's fine.
No, I always do it by evening. I've been doing it from yesterday. Like yesterday also, I did it by evening, right?
All right then.
If you have already, because see, if I upload it to YouTube, then I don't immediately do it, because if you're subscribed to the channel, then you'll get the notification. But then it takes me time for it to share it in the group. So if you are already following the channel, you can see that it's uploaded by evening, or I share it by after like 2-3 hours after that, or maybe 6 hours after that.
All right, sir. All right, sir.
Yeah. So thank you for watching. Have a great day.
Thank you, sir.
Take care.
Thank you, sir.
Thank you, sir.
So thank you for watching. If you have liked this video, you have learned something new, please like and subscribe and share with your friends. All right. Thank you again.